Hey AP Chemsters, this is Mrs. Vanderwey for another edition of the Blank Wall. Today we're going to start section 17.4. I know I'm on page 17.2, but there was a point I wanted to bring up. We were talking about standard conditions, and standard conditions for gases was 1 atmosphere, 1 molar solution for any solutions, and the temperature was 25. And we made that notation for a standard condition for this E naught, okay? And we had said that up until now, every solution was a 1 molar solution. But my question for you is, what happens if we don't have a 1 molar solution? What will happen to the cell potential? So let's go to section 17.4. So here we are, section 17.4, dependence of cell potential on concentration. Again, your standard potentials were all the concentrations were at 1 molar. And what happens then if we don't? What if a variation in concentration? Well, same steps as always, write your balance equation. And notice our good buddy here, Le Chatelier, comes back again. So use Le Chatelier's principle to determine the effect on potential. And it says a shift to the left reduces the potential, and a shift to the right will increase the potential. Wow, does this not sound familiar? That's an awful lot like K, isn't it? Where we shifted to the left, the K went down, and when we shift to the right, the K went up. Same idea. I wonder if there's a link then to E and K. I think we'll find that out later. So in problem number 12, it says for the cell reaction, we have aluminum and the manganese ion reacting to get the aluminum ion and the manganese solid forming. So predict whether that E cell, now notice that the E cell is a little squiggly E, it's the same thing as this E here, is going to be larger or smaller than the E naught. The E naught means it's standard, and this means not at standard. Without the naught, not standard. With a naught, it is standard. So what's happening here? In letter A, we have aluminum is actually larger than the 1 molar. So the manganese ion is standard, the aluminum ion increased. So here's the aluminum ion. And according to Le Chatelier, if I increase this number, it's going to shift to the left. All right, so to relieve the stress. And we learned that back in the equilibrium chapter, chapter 13. And so then what? If it shifts to the left, the potential is going to go down. It's going to reduce it. So here, the E of the cell is going to be less than the E of the cell when it's a standard concentration. So what's going to happen in the next case? Here we have aluminum is in its standard 1 molar, but let's increase the manganese ion to 3 molar. So here is the manganese ion. It is a reactant, and what happens if I increase that concentration? It's going to shift to the right. And what did we say shifting to the right is going to do? It's going to increase the potential. So I would expect the voltage reading, if I'm going to have an increase in the manganese ion, is going to be actually now greater than the E cell. And so this number, at standard. So the E cell is actually greater than 0.48 volts. So that's what I predict will happen. It's just like Le Chatelier again. Now, of course, you know there's probably going to be some math involved, and that's our next section. So how can we calculate the exact number then, quantitatively, for when the cell is not at standard conditions? Well, we're going to go back to our buddy Gibbs free energy, and here we have this equation from chapter 16. And what does this say? It says that the Gibbs free energy that's not at standard condition is equal to the Gibbs free energy change at standard condition plus RT ln a Q. And what is Q? Well, Q is the quotient, the reaction quotient. You set it up like any other equilibrium setup there, and but this time the Q means it's not at standard conditions. It's not at equilibrium. So there's that. And then we have just substituting, what does delta G equal? Well, negative NFE, so that's your cell without it. And it looks like I left out a little naught sign. So let's add the little naught sign. Make a little naught here. And plus RT, L, and a Q. And for some reason, the computer shifted this. This actually needs to be under the RT if you want to fix that. And so here's our equation. So what that says is that the cell potential in a non-standard condition is equal to the cell potential that you get off your charts at standard minus RT over NF, L, and a Q. So if you remember, let me go back to that page again that we started with today. So we're back here again. What's standard condition? 1 atmosphere for gases, okay. 1 molar for solutions, and look at this, 25 degrees Celsius. It is temperature dependent. That standard condition is temperature dependent. So what happens then if we're not at 25 degrees? If we are not at 25 degrees, then we need to use the new temperature and possibly the new concentrations to figure out the effect that the new conditions are going to have on the cell potential. Now, most reactions are going to occur at 25 degrees. That's basically room temperature. And so if you are at 25 degrees C, what this number here has done, it has combined the R value, the T value, and the F value all together, and it simplified your life a little bit. And we end up with 0.0592 over N, because again, that's going to change depending on the reaction, times the log, log, not the ln, the log of Q. So combining all those constants in a sense, even including the transition between natural log and normal log, that's going to be our equation we're probably going to use a lot. So let's scroll down and see what else happens. Now, as the cell discharge, concentration changes and the E cell changes. Is cells spontaneously discharge until they achieve equilibrium. And they say at equilibrium, the cell is considered dead. That Q is now equal to K and delta G is equal to 0. Remember, that's what happened when last chapter, in chapter 16, that if delta G is equal to 0, it's at equilibrium. So if you have a dead battery, that means that you have now achieved equilibrium, where you have a constant rate of reactants making products and products making reactants. That is a dead battery. You'll get no electrical energy from that. So there's a clever saying. I wish I made this up, but I did not. Old chemists never die. They just reach equilibrium. And that's where the joke is on this one. All right, let's go on. So let's see what happens. If we construct a cell with different concentrations of the same metal and ions, but what's the only difference here? Well, on the left-hand side, I have 0.1 molar of my silver nitrate, and over here I have 1 molar of my silver nitrate. Now let's think what's going to happen. When we achieve equilibrium, what is going to happen to our concentrations? Well, as a matter of fact, the concentrations will equal each other. If they're equal to each other, that's when we achieve equilibrium. So how is this going to happen? There is going to be a driving force. Look what it says. There will be a driving force to transfer electrons from left to right. Why will that be? Well, if the electrons are moving in this direction, what's happening here, that the silver metal is actually going into the solution there. So we have silver ions going to increase at that point. That's an arrow up if you can't tell. So if that's the case, and now the electrons are being deposited on the silver metal, that means the ions in solution are actually going to play it out. And so this side, the silver ion will actually decrease. And at what point then will the silver ions increase, and at what point will the silver ions on the other side decrease? Well, you might take a wild guess. It's when these two concentrations end up being equal is when that will stop. Okay, so how is that going to happen? What's going on the left-hand side to increase the silver ions? That the silver metal is being oxidized, and so this is my anode. And over on the right-hand side, my silver ion is being reduced to make the silver metal, and that's my reduction. So until the concentrations are equal, this is the setup, and this is the direction that the electrons will go. So let's check out another solution and see what's happening here. So going down to problem number 14, we have a very, very similar setup. So it says determine the direction of the electron flow and designate the anode and cathode for the cell represented here. Let me give you a few minutes. Go ahead and pause this, and when you are done, come back and visit me again. Okay, so how do we do? Notice on the right-hand side, we have a 0.1 molar, and on the left hand, it's 0.01 molar. So what's going to happen? That this reaction is going to occur so that the concentration of the silver ion will go, or excuse me, the iron ion will go up. That's a 2, by the way. And this is going to happen till the iron plus 2 goes down. So how will I increase the concentration on the left? That some of this iron is going to come into solution to become iron 2 plus. And this is my oxidation, and I can't spell. I was trying to write anode and oxidation together, but that's not a good idea. So this is where the iron is being oxidized to make the ion, and so the electrons are going to go this way, plate here, so that the more iron ions will plate out and on the iron metal, and this is going to then be my cathode. It's actually the same setup as the one before it. So if the more concentrated is on the right, it's going to be reduced. If the more concentrated is on the left, then that will be reduced. But both pictures had the more concentrated ions on the right. All right, so now we're actually going to do some math here. It says describe the cell based on the following half reactions. Notice, here's my half reactions. They're both written as reductions. And notice my ions are not, none of them are at standard molarity. So what they're asking is, what's going to be the cell potential? So let's go ahead and figure out, first of all, which one is going to be oxidized, which one's going to be reduced. They're both written as reduction, so we're going to actually flip the zinc. The zinc's because it's more negative, it's less positive, you wanted to call it that. It's going to be the one that's going to be oxidized. So go ahead and write the total half reactions. All right, hopefully you came up with that. And are these half reactions balanced? The answer is no. So let's go ahead and do that right now too. All right, so notice that we had to multiply the top reaction by 2, and this is very important that you do that. And now write your total reaction. All right, so you'll see here where I found the balance equation. I multiplied 2 through the top, and I left the zinc, I didn't have to multiply that by anything. And so here's our final balance equation. So let's go ahead and plug in the values that we get. So let's start off. What is my general equation? Well, E equals E naught minus 0.0591 over N times log of Q. Okay. And if you look at the standard cell potential is 1.76. minus 0.0591 over my N. I'm looking up here, and it looks like, well, it's 2, and it's 2, so my N is 2. Now look at your log value. Remember, your log is products over your reactants. So notice how I set this up. It is the zinc 2 plus times the VO 2 plus, and I'm going to square that. Why do I square that? Because I have that number there, divided by VO2 plus squared times H, look, to the 4th. So go ahead and now plug in those numbers and see what you get. All right, so here I worked out the problem. When I plugged in all these numbers and squared them and quadrupled them, I got 4 times 10 to the negative 5th as this term here. And then I did all my math, so I got 1.76 plus 0.13, and I got 1.89 volts. Now, does this make sense? Let's go back and look at our initial concentrations. Over here, my reactants are greater than my products, so it's going to shift to the right, and we predicted when you shift to the right that yes, your E is going to be greater than your E naught. It works. Bye.